Have you ever stood in front of a skyscraper so tall that your neck hurts just looking up at it? Now imagine one that rises more than 828 meters into the sky. That's the Burj Khalifa, the world's tallest building, the crown jewel of Dubai, and one of the most ambitious engineering projects ever completed by humankind. But behind its shimmering glass facade lies a story of innovation, precision, and extreme engineering. How do you make a building stand that high in the middle of a desert where wind, heat, snow, and gravity are constant enemies? Today on Rigid Academy, we'll take you deep inside the engineering of the Burj Khalifa, exploring its design, foundation, materials, construction techniques, and the fascinating systems that make it one of the greatest structural achievements of our time. Section 1. The Dream That Reached the Sky. In the early 2000s, Dubai had a vision to transform from a regional trade hub into a global symbol of progress and innovation. The idea was bold. Build not just another skyscraper, but a record-breaking structure that would redefine architectural possibility. This vision became reality when MR Properties commissioned the design from Skidmore, Owings, and Merrill, the same firm responsible for icons like the Willis Tower in Chicago and One World Trade Center in New York. The architectural concept was led by Adrian Smith, while the structural design was developed by William F. Baker, one of the world's leading structural engineers. Their challenge? Create a structure that could rise over 800 meters while remaining stable, elegant, and economically feasible. The Burj wasn't just meant to be tall, it had to be livable. The building includes residential units, offices, restaurants, observation decks, and even a hotel designed by Giorgio Armani. So the engineers had to blend strength, flexibility, and functionality into a single design. Section 2. The structural system. The buttressed core. At the heart of the Burj Khalifa's design is one of the most remarkable structural systems ever created, the buttressed core system. Imagine a central hexagonal concrete core surrounded by 3 wings arranged in a Y shape. Each wing buttresses or supports the other 2, creating a triangular configuration that distributes both gravity and lateral loads efficiently. This system allows the tower to resist strong winds and seismic forces, while also providing vast open floor spaces for residential and commercial use. The central core acts as the spine of the building, while the wings stabilize it from every direction. As the tower ascends, its shape steps back in a spiraling pattern, reducing the wind forces and minimizing vortex shedding. This tapering not only enhances the building's aerodynamics, but also creates its iconic, sleek silhouette. The buttressed core concept became so effective that it inspired later super-tall towers, including the upcoming Jeddah Tower in Saudi Arabia, which aims to surpass even the Burj Khalifa in height. Section 3. Deep foundations in the desert. When you build something that tall, the foundation must be extraordinary. Beneath the Burj Khalifa lies a massive reinforced concrete mat, nearly 3.7 meters thick, supported by 192 board piles that extend about 50 meters into the ground. Each pile is 1.5 meters in diameter, made of high-strength concrete capable of withstanding enormous compressive forces. These piles transfer the tower's weight, which exceeds 500,000 tons, safely into the underlying sandstone and siltstone layers of Dubai's desert soil. Because the site was near the Persian Gulf, engineers had to deal with high groundwater levels and corrosive conditions. To prevent deterioration, they used special protective coatings and concrete additives resistant to chloride attacks and sulfate reactions. Before construction began, extensive geotechnical investigations and pile load tests were performed to ensure that the soil could bear the immense loads. The results confirmed that the foundation would remain safe for centuries, even under extreme conditions. Section 4. Concrete at record heights. Most of the world's tallest skyscrapers use steel, but not the Burj Khalifa. This giant is built primarily with high-performance reinforced concrete, a decision that surprised many engineers at first. Concrete was chosen because it offers superior compressive strength, thermal resistance, and cost efficiency in Dubai's harsh environment. However, pumping concrete to such heights was one of the project's biggest challenges. Engineers developed a custom concrete mix that could be pumped vertically more than 600 meters, a world record at the time. The mix contained fly ash, silica fume, and superplasticizers, which improved flowability and reduced heat generation during curing. Concrete pours were scheduled only at night, when temperatures were lower, and every batch was monitored using thermal sensors to ensure uniform strength development. The final product was concrete with a compressive strength exceeding 80 megapascals, giving the Burj the solid backbone it needed to rise into the sky. Section 5. The Wind Challenge. When a structure rises this high, wind becomes its most dangerous adversary. Engineers had to ensure that the Burj could withstand wind speeds of up to 240 kilometers per hour. Over 40 wind tunnel tests were conducted in Canada to analyze aerodynamic behavior. Engineers tested scale models to measure vortex shedding, pressure distribution, and lateral motion under different conditions. The Burj Khalifa's Y-shaped floor plan wasn't just aesthetic, it was the key to taming the wind. The staggered setbacks cause air vortices to break up inconsistently, preventing resonance and reducing oscillation. This unique aerodynamic approach allows the building to remain remarkably stable. At the top, even during strong winds, the movement is less than 1.5 meters, a barely noticeable sway for occupants at such extreme heights. Section 6. Construction Logistics and Speed. Construction of the Burj Khalifa began in 2004 and was completed in 2010, remarkably fast for a project of this magnitude. The project involved over 12,000 workers and engineers from more than 100 countries. Work progressed at an incredible pace, roughly one new floor every 3 days during peak construction. A specially designed climbing formwork system was used to pour the concrete core continuously, minimizing downtime. As the structure grew, tower cranes, capable of lifting loads over 25 tons, were anchored directly to the building itself and climbed higher as new levels were added. Precision was critical. Survey teams checked alignments using GPS and laser systems to ensure vertical accuracy within millimeters. The margin of error for a building of this size was almost zero. The uppermost spire, made of structural steel, was assembled inside the tower and then jacked up into place using hydraulic systems, a process that required perfect synchronization. Section 7. Cladding, Elevators, and Systems. The Burj Khalifa's exterior is clad with more than 26,000 glass panels, forming a shimmering curtain wall designed to resist Dubai's intense heat. The glass panels are coated to reflect sunlight while minimizing heat gain, keeping the interiors cool and energy efficient. The building is also equipped with double-deck elevators that travel at speeds of 10 meters per second, making them among the fastest in the world. There are 57 elevators and 8 escalators, all engineered for smooth operation and minimal vibration. Water supply is another engineering feat. Every year, the building consumes over 250,000 gallons of water daily, delivered through a pressurized piping system that maintains consistent flow up to hundreds of meters. The Burj's air conditioning system uses a unique method. Chilled water is produced at a central plant and pumped throughout the tower. The system even condenses humidity from the hot air, producing nearly 15 million gallons of reusable water annually. Section 8. The Spire and Lightning Protection. The spire atop the Burj Khalifa adds nearly 200 meters to its total height and houses communication and broadcast equipment. Made of structural steel, the spire was assembled inside the tower and later lifted into position, a process requiring extreme precision. Given the tower's height, lightning protection was a serious concern. Engineers installed a network of copper conductors and grounding rods to safely direct lightning strikes into the ground, protecting both the structure and its occupants. The spire also acts as an architectural crown, symbolizing the merging of engineering and art, a modern-day pinnacle of human achievement. Section 9. Performance, Maintenance, and Legacy. Since its completion, the Burj Khalifa has withstood Dubai's extreme weather, from scorching 50-degree-Celsius summers to sandstorms and high winds. The building undergoes continuous monitoring using structural health sensors that measure strain, movement, and temperature variations in real time. Maintenance crews, known as Spidermen, rappel down the glass facade to clean windows and inspect joints, a process that takes about 3 months to complete one full cycle. But beyond its technical marvel, the Burj Khalifa stands as a symbol of what engineering can achieve when vision, science, and innovation come together. It inspired a new generation of architects and engineers to push the limits of what's possible. Conclusion: the Burj Khalifa is more than just a skyscraper. It's a statement that even in the harshest environments, human ingenuity knows no limits. From its buttressed core and record-breaking concrete to its aerodynamic design and engineering precision, every part of this structure tells a story of creativity and determination. So next time you see the Burj Khalifa shining in the desert sun, remember, it's not just a building. It's the result of thousands of minds, millions of hours, and decades of progress, all converging into a single monumental achievement. Thank you for watching Rigid Academy. If you enjoyed exploring the engineering behind the world's tallest building, don't forget to like, subscribe, and check out our full series on engineering wonders, mega and historical structures, where we uncover the secrets behind the greatest structures ever built.